Chapter 6, Number 41. A 3.50 kilogram block on a smooth tabletop is attached by a string to a hanging block of mass 2.8 kilograms, as shown in the figure. The blocks are released from rest and allowed to move freely. A, is the tension in the string greater than, less than, or equal to the weight of the hanging mass? And then B, find the acceleration of the blocks, and C, the tension in the string. So A we can do qualitatively without having to do any kind of number of things, and we think of it this way. When we let this go, let's give them some names. So we're going to call this one M1, and we're going to call this one M2. Block 2 will want to fall, and it will be held up at least a little bit by the string, so there'll be tension in the string. The tension in the string will pull on block 1, and there is no resistance because, as we see here, it's a smooth tabletop, which means no friction. So there's nothing to resist it moving. So then block 1 will move over to the right, and block 2 will start to actually descend. Since block 2 is actually descending, it means the tension is not counteracting gravity sufficiently, so the tension will have to be less than. All right, we'll come back to that and verify it when we get the tensions, but it will be that it's less than. And then for B and C, we'll do our usual game, and we'll say, let's do a free body diagram for each object. This is object 1, and this is object 2. Object 1 has a weight pulling down on it, which is Fg1, and object 2 has a weight pulling on it called Fg2. And then there's, of course, a normal force pushing up from the table, which we're just going to call Fn. And then there's a tension in the string, and the tension in the string pulls object 2 upward, but it also pulls object 1 rightward. And then, because they're attached by an ideal string that can't stretch, for every centimeter that block 1 moves over, block 2 moves down, and therefore they have the same velocity at all times, which means they must have the same acceleration at all times. And that's what we're going to try and find. Okay. From the diagrams, we get 3 force equations. The force on block 1 in the x direction is just Ft, and the force on block 1 in the y direction is Fn minus Fg1, and then the force on block 2, which is also in the y direction, I suppose, is Ft minus Fg2. And then from Newton's second law, we have that the sum of the forces on block 1 is m1 times the acceleration it feels, and the sum of the forces on block 1 in the y is m1 times the y acceleration, which is 0, and the force on block 2 is m2 times the acceleration of 2, but 2's acceleration is a downward, so we pick up a minus sign. So, using some basic math identities, f1x is equal to f1x, of course, and so we have that ft is equal to m1a, and f2y is, of course, equal to itself, and that tells me that ft minus fg2 is m2 times minus a. Notice we have a third set of equations, that f1y equals, of course, sum of f1y. That ends up not contributing anything. It's true, it just doesn't end up having any role in this problem. There's nothing that connects us to that. There's nothing we really care about the normal or the weight of block 1. So if we take the ones that we have and put them together, though, we can see that this equation into here gives us that m1a minus m2g equals minus m2a. And then we can add m2a to both sides, and add m2g to both sides, and we end up with m1a plus m2a equals m2g, and then we can factor out the m1's, or sorry, factor out the a and have m1 plus m2 times a equals m2 times g. Then we have that a is m2 over m1 plus m2 all times g, which is sort of convenient, which ends up being 2.80 kilograms over 3.50 kilograms plus the 2.80 kilograms, all times 9.81 meters per second square. And this is 4.36 meters per second square. Now it's easy because we have an expression that says that the tension is just m1a, so it's 3.5 kilograms times 4.36 meters per second squared, which is 15.3 newtons when rounded to the appropriate amount. Let's notice that m2g, the weight of the hanging block, is 2.80 kilograms times 9.81 meters per second square, which is 27.5 newtons. So as predicted, the tension is in fact less than the weight of the hanging block.